name? Because I've been asked about it at least from 3 different people. So please say that 3 times and we'll get it.
Guillochon, Guillochon, Guillochon. So if you know the guillotine, you know, they chop people's heads off. Just think the first part of that, and then chon, like really French. So Clement could probably tell me how to do it better. I've been corrected by French people on my own last name. Yeah.
Okay.
Do you think we can move this? I think I'll be okay. Right. Okay, so first I wanted to commend Svi on a very clever name for the circularization. So I Googled Jerusalem bagel just to see what they look like. I've never been here before. And I think it's actually a really good food, as best of a food descriptor of TDEs that you can come up with. But I wanted to make one comment, which was that I think for now, we haven't focused too much on what happens when we exceed Eddington. And including the radiation physics, I think, is one of the harder things to do. And so Eric Coughlin with Mitch Begelman had a paper on zebras. So I think if you wanted an inclusive model to account for the sub and super Eddington, it should really be the Jerusalem Begelman model. I think that'll be a little bit more inclusive. So I can see Svi kind of giving a half smirk, so maybe. Okay. So I'll be talking about today, I think, an aspect of the problem that no one else has done quite yet, which is to include magnetic fields in the star originally being disrupted, and just trying to figure out if that has any dynamical effect on the disruption and the consequences of including a magnetic field in the star to begin with. I think rightly so, most of us focus on the circularization afterwards because that's what produces all of the light. But this actually has implications for jet formation because you may be starved of flux, which is necessary to produce the jet. And it also could have implications for the magnetic fields of stars that are partially disrupted by black holes. In principle, this process could lead to an amplification, which could give you stars that are highly magnetized if they've encountered the black hole previously. This work was done primarily with Mike McCourt, who's now at Santa Barbara and was my office mate last year. So the brief outline, I'll just talk about magnetic fields in stars really briefly. I'll do a tiny overview of tidal disruptions, even tinier here because everyone knows what I'm talking about, hopefully. I'll talk a little bit about magnetic fields and why you should care, and I'll show you some preliminary results. Okay, so magnetic fields in stars are typically very weak. It's something like 1/1,000,000th of equipartition in something like the sun. The sun is our best laboratory for studying magnetic fields because we see very high resolution pictures of its surface, all these prominences, and we also can do very detailed asteroseismology on the sun. But we really can't probe very deeply into the sun's structure to figure out what the internal magnetic field looks like in a great level of detail. We have some idea for how the sun is, its internal motions are going from the asteroseismology, but the magnetic fields are carried along by those motions, and it might result in a very complicated structure that I think is pretty much only known by looking at computer simulations of such stars. So that's true, yes. Yes. So in giants, actually giant stars being disrupted, this has perhaps huge implications, especially since they're more magnetic, and because there is a possibility that a giant star could have form the streamer that G2 is a part of in principle. So if that were the case, the magnetic field configuration inside that debris could be very important. So this is just showing some examples of magnetic field configurations in some magnetic, more main sequence-y type stars. So this is an example, magnetic subset of A stars called AP stars. They have very large convective flows, roughly star scale, and you get this sort of tangled spaghetti-like structure inside the star. Not really a strong dipole component, very mixed. Other people have done simulations of these, found even larger scale helical twists in these fields. And this is sort of an ongoing area of study, so I don't think people have really converged on what the magnetic structure really is, but these are what the simulations are showing, and they're very interesting. Another example is of a rapidly rotating sun-like star, so this could be something like the sun shortly after it gets onto the main sequence and still has a significant amount of rotation. There you get these giant wreaths of counter-directional magnetic fields on the north and south above the equator in the star. So very fascinating internal magnetic field structures you can get, but the point was just to show that you can get variety. You can also have in irrotational stars something that vaguely resembles a dipolar configuration interior as well. But the real answer is that we don't really know for a large fraction of stars what this looks like. So there's really kind of two flavors for currently magnetic stars. There are those where the fields are generated by internal motions and actively sustained by those internal motions. So that could be protostars, AP stars, dwarf stars, red giant stars. Or they had large internal motions in the past, and those fields are now frozen in. So they're sort of relic fields from a time when you actually had significant motion in those objects. So that would be magnetic white dwarfs or magnetars. Interestingly, from this review paper on magnetic fields in stars by Reisenegger in 2009, the maximum flux value for all stellar types is 10 to the 27.5 Gauss centimeters squared. So that number is the same for the most magnetic magnetars as the most magnetic red giant stars. And it's a very interesting value. Okay, so tidal disruption is brief. Star passes by the black hole, gets tidally destroyed. The only reason why I want to show you this slide is that in some cases, if the tides are weak, you can get a surviving core in the center, even if you remove something like 50% of its mass. And those encounters are more common, not just because they happen further away from the black hole where the rates of disruption are a bit higher, but because you probably get multiple encounters per star when this occurs. It'll run by the black hole several times, each time losing a little bit of mass. So this is a simulation, pure hydro, just showing a partial disruption of a star. Just to give you an idea of what this looks like. You get your two tails that are launched out. The core experiences some decompression during pericenter approach, but then recollapses, and then actually starts to pull in these arms back onto itself and reaccrete some of its own matter. So you end up with this actually highly turbulent, rapidly rotating core. And if you also notice is that the streams are not feeding directly onto the core, they're kind of offset. So it has significant angular momentum. And if you look, you can see these sort of spiral shocks moving out. It's a little hard to see with the light level. But that's actually a redistribution of angular momentum. Oh, you can see it over there. Great. Yep.
On the screen.
Yes, I think one of those switches was the projector, because now. Okay. Yes. Okay. I can probably disconnect and reconnect if it's. Is the projector on? Yeah. I think the projector is actually powered off. Great.
Not yet?
Then we have to wait for this to warm up. I remember Elliot Quader came to Santa Cruz when we had a power outage during the middle of his talk, and he just started pantomiming in front of the audience. He was doing some sort of magnetic instability thing. It was pretty entertaining. So I might start spinning around soon. Yeah, so these lights now are like directly illuminating the screen. That's why it's not very visible. All right, well.
You're being interrogated now. Okay, this would work, but I'm calling someone quick.
Yeah. Okay. Well, so now we're going to look at a full disruption, which will go a lot faster just because I didn't dump out so many frames here. But just very simple. It just gets obliterated and stretched into an elongated stream whose width is controlled by self-gravity, surprisingly enough. Okay, so why should you care? So I kind of mentioned this in the intro. We could potentially amplify the magnetic fields in partially disrupted stars. We want to know if we can deliver enough flux to the black hole to power the jets. And if that's the case, or even if that's not the case, we're interested in what is the structure of the magnetic fields that actually feed the black hole post-disruption. So the idea was to kind of characterize what happens in a disruption for a few examples, a few different internal magnetic field configurations to see if we can get the answers to those questions. And it would be valuable information for people who are mapping their initial conditions into these circularization calculations. Okay, so my code of choice is Flash, which is my bread and butter for the past several years. The solver that I'm utilizing is an unsplit staggered mesh solver utilizing constrained transport. So the big problem that a lot of numerical codes have is conserving Maxwell's simplest equation, which is that div b equals 0. In SPH codes in particular, this is very difficult to do. Seems like the lights are off now, so yeah, that's good. So because I believe in exposing one's dirty laundry, I'll say that Flash does obey this expression to numerical precision when you don't use the refinement operations in the calculation. The refinement is supposed to conserve div b, but there's some sort of very subtle bug where every once in a while when you de-refine a block, it will spuriously generate some div b. It's fairly small, maybe 10 to the minus 3 the field strength on these artifacts. But the current workaround is really to just de-refine as little as possible, and I'm trying to work with the Flash people to try and resolve that. That being said, it is small, and actually a lot of the other methods I'll talk about have order unity errors and divergence. Okay, so the initial conditions, we have a partial disruption and a full disruption, so beta 0.7 and 1.5, polytropic index 3/2, which is approximately a fully convective star. We see the magnetic field via its vector potential because we can ensure that at least the initial conditions have no divergence. The star initially has 100 cells in diameter. We start out with a very strong magnetic field for something like the sun, mega-Gauss fields, simply because we didn't want the beta value to be too extreme, the magnetic beta. And we also only define the field within the star, just because the Alfvén speed in the vacuous fluff you have to place outside of the star would be really huge if you placed it there. Okay, so I'm going to show you another movie. This is again a partial disruption. This one has magnetic fields in it. So this is just showing you the density again. And on the surface, it doesn't look tremendously different from the other simulation, which was slightly different conditions anyway. But inside, there is a tangled magnetic field, which looks like this. So it is intensity. So magenta is the most intense magnetic fields, and I think blue is the least intense magnetic fields. It goes from megagauss for the magenta to maybe 100,000 Gauss for the blue. So the way we initialize it is that we maintain the same magnetic energy fraction throughout the star. So on the surface it has weaker fields than it does in the core. And that is a bit of an arbitrary choice because in real stars it does vary as a function of radius. So this is just showing a movie of what's going on with the magnetic field inside that star when it is disrupted. So if you look closely, you can see that there are these two vortical structures that form shortly after the disruption when the core recollapses. So you can see them kind of there and there on both sides. And I'll pause it now. So those two vortexes last roughly a dynamical time, so maybe one orbital period of the surviving core. And you'll notice two things. One is that inside the core, things look fairly tangled aside from those two large vortical structures. But in the arms, you can see that the field lines are very, very straight. They've straightened out quite a bit. And the initial magnetic field configuration was totally random relative to the direction that the star came in at periapse. So despite that, you don't see much of an imprint of that randomness in the arms. And in density, you can see that these vortexes are actually two underdensities within the structure of the star that are really, really quite low relative to the core. So really the star kind of deforms into a double-holed donut during this phase. So why do you see that field straightening in the arms when you see it just tangling up in the center? Well, it's just simply flux conservation. So the star is being primarily stretched in one direction. So the cross-sectional area through the star is remaining roughly fixed. So the amount of flux going through that area is remaining roughly fixed. So the magnetic field strength is not changing very much for field lines that are parallel to the direction of stretching. For field lines that are perpendicular to the direction of stretching, you're taking the same flux and you're stretching it out through a much larger area. So what ends up happening is that the field is tangled, but the components that are perpendicular to the stretching are being degraded significantly. So then when you look at the flux after the disruption, all you see is the parallel component. So this is what the field geometry looks like in the star after it's sort of in this elongated case. So this is a fully destroyed star now. So the top is the top view and the bottom is the side view of these fields. So we'll just scroll past what that looks like. So very, very straight, stretched and elongated along the direction of stretching. And that's pretty interesting, I think. Because remember, we started out with random initial conditions. It could have very well been the case that the field lines were perpendicular to the direction of stretching, which would be interesting, I think, if you're interested in powering a jet. Okay, so just a schematic showing this. So in a partial disruption, that core is twisting around. It's pulling in matter from those two arms that are accreting onto the core, and it ends up giving you a very tangled, twisted field. For the full disruption, it's pretty boring. It just sort of stretches and takes the field and exaggerates it in that direction. So this is now showing magnetic beta. White is basically gas pressure dominated. Black is magnetic dominated. So if you look at this movie, you can see how tangled the structure is inside the star. You also notice that inside the star, the magnetic field is not dominating the gas pressure in most places. It's still pretty white. Actually, black is where they're equal to one another. In the arms, however, you can see that it's completely black. So the magnetic field is starting to dominate in the arms resulting from the tidal disruption. So I'll just show this one more time. If you pay attention to the arms, you can watch them change color. They go from sort of a orange red to a dark black. Yes?
Now your scale stops at log 0.
That's right.
Does it go negative?
It does go a little bit, I guess, super virial in terms of the magnetic field strength, maybe a factor of 10 times larger. It does become magnetically dominated. The reason for it is that as you stretch the star, it adiabatically degrades the internal energy, but the magnetic field strength is not going down. So that's basically what happens. So now we'll just show a CAT scan through this through this star. So this is basically showing you field going out of the page and into the page as red and blue colors, respectively. So what you'll notice is that it does have a relatively complicated cross-section. It kind of looks like a face. The reason for that, that's related to basically the random parallel component to the stretching. Because remember, we started with a random field. And roughly you can see that there's just as much flux going into the page as out of the page. So what this really is a giant loop. It's a giant field loop that stretches from the core all the way to the tip of the stream and back. And if you remember the elongated stream I showed you before, that was basically the structure. This is the top-down view of what the perpendicular component of the field looks like after the disruption. So you can see quite a bit of substructure, lots of reversals of the field. Okay, so now let's compare. So we're showing now a difference between a pure hydro and a field with and a run with magnetic fields included. The one with the slightly fatter streams is the ones with the magnetic field included. So what you can notice is that actually the inclusion of the magnetic fields gives you an additional pressure component, which causes the streams to be a little bit wider than they would have been with the neglect of that particular contribution. Now what I'll say is that for real disruptions of sun-like stars, the magnetic field strength is 1,000 times less than what I had assumed in these initial conditions, because I really wanted to maximize the effect. So really only for very magnetized stars would we expect this to be significant, but it is interesting that you can see it quite visibly in the density structure. All right, so let's talk about energetics. The important lines to look at here really are the magnetic energy. So this one here is a partial disruption. This one is a full disruption. And you can see that there is an amplification of the magnetic field in the partial disruption by about a factor of 10. The field starts to unwind at late times. It's not clear if that's numerical or physical. Yeah. Oh, 3 minutes. And that's basically due to those vortices that you saw form shortly after the disruption. That's where most of this amplification occurs, is when those vortices form. Once the vortices go away and the star settles down, you stop seeing amplification. In the full disruption case, the magnetic energy has a few blips in it related to the fact that the volume of the star is changing in a sort of complicated way during periapse. And then fascinatingly, you can see the magnetic energy is declining slowly, but not as quickly as the internal energy is. So you can see that if you let this run for infinite time, eventually the total magnetic energy in the stream will be greater than the internal energy of the stream. So that tells you it's going to become magnetically dominated. Now, if you start with a star with a lower magnetic field initially, these curves will be down lower to start with, and it will take a longer amount of time for those two to become comparable to one another. So we tried a few different configurations and strengths just to see if we can get any trends. These are all partial disruptions. The dashed lines show a dipolar field configuration initially, where we put it the dipole perpendicular to the orbital plane. And in all cases, you see sort of a level of 10 amplification of the field. It also seems like we get a little bit more amplification in the cases where we start with a slightly weaker field to begin with, but it does seem like it's relatively close to converged, in the sense that if we increase the field strength, it's not changing the amplification dramatically. My guess would be is that if we went to really extreme fields where you start getting comparable to the magnetic internal energies, that's going to prevent the growth of the field significantly. So it seems like we're getting maybe a factor of 10 increase. That's interesting, but it's not as interesting as I think it could be, right? We were kind of interested in maybe generating a magnetic star out of nothing. But it seems like even if we give it a good head start, it doesn't actually get there. Okay, so just briefly comparing to analogs. People have done simulations of neutron star mergers, white dwarf mergers with magnetic fields in them. That's basically the closest analog we have to this. This is sort of a star merging with itself, if that makes sense. And in those calculations, so this neutron star merger calculation, the amount of amplification that they see there is on the order of 10 to 5, and it's resolution dependent. So in the white dwarf merger cases, they use a method that does not conserve div B. And if you look here, the magnetic energy goes from 10 to the 24 ergs to 10 to the 47 ergs in their calculation. So it goes up by 23 orders of magnitude. So it's quite a stark difference between the two methods of doing this, and it makes me question a little bit the methods that don't conserve diff-B. Okay, I'll skip this. Okay, so primary findings are that the magnetic fields basically maintain their original strength in the tidal debris. Eventually, the magnetic energy density can become comparable to the internal energy, which means that it actually could affect the width and the dynamics of the stream. We start out with a much stronger field than normal, so you have to keep in the back of your head that these kinds of things might happen at later times in real disruptions. We assume magnetic geometries sort of arbitrarily and found pretty similar results independent of those geometries that we assumed. So I just wanted to say that before we actually finalize this, we were working on one double resolution simulation, which you can see in the background here. So each pixel that you see there is an actual voxel in the calculation, so it's very, very high resolution. Unfortunately, NASA Pleiades has been having technical errors the past 6 months that have, this is the last snapshot I have of that before we need to restart again. So if the neutron star calculations that showed a greater increase in amplification as you increase the resolution are true, we might expect to see that here. So stay tuned. And I think we need to do a bit more quantitative analysis. We have sort of a basic idea of what it does qualitatively, and it seems to make total sense when I explain to you the flux conservation. And in principle, we didn't need to run a simulation for that. So we kind of want to get more specific numbers for these things I'm describing. So, thank you.
If you ID that, you will lose time to yes.
Do you see any magnetic reconnection when the star's tidal speeds, or what evidence? Do you have any evidence?
I don't think so. I don't think we see, if there was reconnection, it would be numerical in the calculation anyway.
Numerical error?
It would be sort of when two fields of opposite directions. It's physical in the sense that that's what really happens, but the scale that really happens in reality is much, much smaller than what we can resolve in the simulation. So,
Do you see a significant difference between the two beta encounters that you were doing?
in terms of the amount of numerical reconnection, I don't think so. It does seem like flux freezing is a pretty good approximation to how the energetics are changing. So for instance, the magnetic energy density seems to go pretty well with the volume of the star. So that suggests that actually the density is not changing dramatically much in response to numerical reconnection effects.
One long-term signature of such an event would be to have a rapidly spinning core. So I'm wondering, the realignment of the magnetic field following the particle disruption, would it increase or decrease the magnetic radiance, thereby, affecting the longevity of the signatures?
Yeah, so one thing with the partial disruption cores is that they basically rejoin the Hayashi track in a sense. You're kind of revitalizing the star. You're dumping in a ton of extra energy above and beyond what it has from its own nuclear energy that it produces. So it evolves, I think, very similarly to a star that's going down the Hayashi track. And those stars will start out with strong magnetic fields as well, and I think it'll break in a very similar way to the way those stars do. Yeah, that's right.
It will be at least at that point less effective in breaking because the universal breaking to maximum breaking.
That's true. There will be some breaking, but it might be reduced relative to a dipolar configuration. I actually don't know for protostars how dipolar the field really is inside of them. Maybe someone else can answer that question.
I have a question kind of related to Carl's that has to do with building up a strongly magnified star. So this factor of 10 amplification you see in the partial tidal disruptions, is that driven by the returning tails that matter, or by the nonlinear modes excited in the surviving core itself? Because if it's the latter, you can imagine a sequence of weaker tidal encounters
Right.
that build up the field.
That's right. That's right. So if it's a factor of 10 every time, then if you want to build up 3 orders of magnitude in strength, you would have 3 encounters with the black hole to build it up. The one thing that makes me worry is that the magnetic energy does have this slow decline at late times. And I think what's happening is that you've wound up the field considerably during the disruption, and it's starting to unwind and basically tap into that magnetic energy and sharing it with the kinetic energy of the star. So that's basically leading to a slow drainage of the magnetic field in the star. And it's not clear to me if the level of decay that we see is resolution dependent. So we have run 1/2 resolution simulations that look pretty similar to these. So I'm fairly confident that what we see here is physical, but I'm not entirely sure yet.
Well, thank you very much.